Let's talk about integration in the formal sense as a Riemann sum, as a sum of a bunch of little rectangular areas. I'm going to talk about writing integrals as limits of Riemann sums in the context of a particular function right here. So what I'd like to do with you right now is to work to write an expression, a correct expression that expresses this limit as the limit of a Riemann, this integral as the limit of a Riemann sum. First, we should probably dissect the pieces of the integral that I wrote up here. So this one down here, we typically call that A. We typically call this pi here B. And those are the bounds of integration. So A to B, so we read this as the integral from 0 to pi. That's how we narrate it. And those are the bounds of integration. So the interval A, B is depicted in this symbology with A as the lower limit and B as the upper limit. Okay, so those are the bounds of integration right there. The bounds of integration, left and right. The thing inside here, this is what we call the integrand. And it's the function that we're going to integrate, the function that we want to find the area underneath. And this little dx right here is the differential. And that represents an infinitesimal amount of x that we're going to multiply against a height determined by the sine of x. So this right here represents the width of an infinitely thin rectangle of height determined by the sine of x at the position x for the corresponding rectangle. Okay, so those are the various pieces of this expression right here. And the formal limit definition says that this expression right here is equal to the limit as n goes to infinity. And you'll see it both lowercase and uppercase, and depending on sources that you're reading. Today I'm working with lower cases. In principle, it doesn't matter. Of the sum of f of x sub I times delta x. And where am I summing? I am summing from j equal... Oh, I used I, so I think I'd better use I again. I don't know. The name of it doesn't matter. It's what we call a dummy variable. This I right here is called a dummy variable because it doesn't... The name of it doesn't matter at all. So I equals 1 to n. So this expression right here is the formal definition of what this thing is. So how do we get a hold of this? The answer, the number that represents the area between sine of x and the x-axis between 0 and pi, is by doing this limit right here. Let me go ahead and draw a quick little diagram that has some axes. I think I'm going to use blue for my axes. So here's an axis, here's another axis. This is the x-axis, this is the y-axis. Here's 0, here's pi. So there's my interval from 0 to pi. And the function sine looks like that. So we're finding this area inside here, and we're doing that by breaking it up into a bunch of little rectangles whose height is determined by the function itself, and whose width is delta x. And in the limit, as n goes to infinity, we have infinitely many rectangles right here, and they're all going to be infinitely or infinitesimally narrow. So these infinitesimally thin rectangles, and this delta x, which is not infinitely thin, turns into dx in the limit. So in the limit, delta x turns into dx. So this thing right here is the integrand, it's f, and it's also f right here, f of xi. delta x. I'd like to specify what delta x is in this particular context. So n is the number of rectangles, and we're taking that as we have infinitely many even width rectangles, and I'm summing over that finite number of rectangles, except in the limit, only infinite in the limit. So I'm summing over a finite number of rectangles. Finite number of rectangles means that this right here is some finite, not infinitesimal number. How wide is delta x? Well, the total width of this interval is, so delta x, the total width of that interval is pi minus 0 over n. That's delta x. My xi's, I want to make that concrete. What are my xi's? I'm going to do a quick little helper diagram over here. I've got the interval from 0 to pi, and I've broken this into 1, 2, 3, until I get to n intervals. Remember that these points are labeled. Remember that these points are labeled with subscripts as little x values. So 0 is what we call x sub 0. Pi is what we call x sub n. The next one is x sub 1, x sub 2, all the way until we get to x sub n. We're keeping this generic, though. I'm not specifying what n is because I'm going to take it to infinity. This thing right here is 0. This width here, the width of one of these things is delta x, which we know is pi over n. So these x1, the space between x1 and x0 is pi over n. So x1 is equal to pi over n. x2 is equal to pi over n times 2. And these are all offset from 0. So there's like a plus 0 right here that I'm not writing, because that's where I'm starting, is plus 0. So I'm adding a delta x, a pi over n every time I step over. And in general, x sub I is equal to pi over n times I with a plus 0 that I'm not writing. And be careful, there's no parentheses around this. It's pi over n times I plus 0. Plus 0. Okay, so we're able to figure out a formula for what x sub I is. So I'm going to erase my plus zeros. This is the thing that I needed to go right here. F is sine of x. F is the function that I'm integrating. So this is the function f. This is f of x. So putting this expression right here, pi over n, into f, I'm going to have the sum from I equals 1 to n of sine of pi over n times I. So this right here represents, I drew my rectangle wrong. This right here represents the area of the rectangle determined by right endpoints. There we go. Am I acting that's right? Because it's x sub I, not x sub I minus 1. It doesn't bear talking about at this particular point why that is. Okay, so the height of a rectangle is determined by this. The width of the rectangle is determined by that, where this value right here that we use to determine the height of the rectangle, right? See how the height matches the height of f right there? That's the value x sub I. So above, x sub I lives the function doing whatever it's going to do, and then this defines a rectangle right there. So this f of x sub I times delta x is the area of this rectangle. That's the area of this rectangle, and I've got a bunch of them next to each other, and I'm going to sum them up, and that approximates the area under the curve. And as I have infinitely many of these rectangles, the area in the rectangles converges to the curvy area that I seek to compute. But I don't have a handy-dandy formula for. So I think to finish this thing off, let's think about erasing. I think to finish this thing off, I think all I want to do is go the limit as n goes to infinity and put that in the front there. Yeah, I do want to erase. Okay, so I'm done with my helper work to determine what that was. And if I wanted to make that equality completely explicit, I'm going to rewrite that down here. God, that is a really atrocious limb, isn't it? If I could, like, take a magic pill that would, like, make me a better handwriting, I would totally do it. There we go. There's a stool there. Let's eliminate this minus 0 here also. There we go. Okay, so what is that? That's the integral from a... Nope, that's the integral... I have concrete numbers. I know. Concrete numbers. That's the integral from 0 to pi of sine of x dx. Formally is defined to be the limit of this sum. Heights of rectangles, delta x. Now, we have one more thing I want to discuss before I call it good. And that's the fact that, see, look at this pi over n that multiplies the sine thing right here. The sine here depends on I. See how that depends on I? Right? Like if you change I, then the sine value changes. But if you change I, this pi over n, it doesn't change. The pi over n just multiplies each one of these sine things here. So that's essentially a multiplicative constant against every single one of these terms. So, as an additional simplification, what I'm going to do is I'm going to take that pi over n and I'm going to put it out front. Not of the limit, but inside of here. I can't take it outside the limit because it does depend on n. So that was pi over n. Boop. Pi over n. Right? I can't go all the way out because it depends on n. Look, pi over n. I can't pull that out because then it doesn't... Then I'm not limiting it anymore. Okay. So that's the conversion of an integral into its formal limit of a sum definition is the limit of a Riemann sum. Thank you for watching. I hope you have a lovely day. Bye.